In this presentation, we're going to be covering the use of linear algebra in search engines. For a little background, as the internet began to grow in popularity and massive amounts of searches began to flood in, programmers began to realize they needed a more helpful and efficient way to organize results pages rather than simply returning them in alphabetical or random order. This is when the idea of search engine results pages, also known as SERP, rankings began to take over, and factors such as the use of keywords or page domain authority were used to order the results shown to a user. In order to do this as efficiently as possible, programmers utilize linear algebra and matrices.
So the way PageRank works is that every web page on the internet is a node in a network of all the other web pages, and they're all connected by links, but not every node connects to every other node. So we make an incidence matrix that shows the connections that each web page has with another web page. To find the worth of a web page in a network, we use the equation AX equals X, where A is the incidence matrix that we made, and X is the vector that holds the worth of each web page. So to find what X is, we have to find the eigenvector of A that goes with the eigenvalue of 1. So in the incidence matrix, each web page that a specific web page connects to is adjusted for how many other web pages it connects to. So say a certain web page is linked to 3 others, each value in the incidence matrix will be 1/3.
Now we will be doing a MATLAB example problem. So this problem is asking to determine the importance of these 6 pages relative to each other as if they were results from a certain search. So page 1 links to page 4 and page 6, page 2 links to page 3 and page 4, page 3 links to page 1, 2, 5, and 6, page 4 links to page 5 links to page 1 and 2, page 6 links to page 4 and 2. In order to determine the rank of importance of the pages, we need to put this information into an incidence matrix. So in the matrix, each row and column corresponds to a certain page. The column represents where each page is pointing, and the row represents which page is pointing towards it. So column 1 shows where page 1 points, and row 1 shows which pages point to page 1. The amount each page points will always add up to 1. So if a page points to 2 places, each place will receive 1/2 as the entry corresponding to the occurrence. So row 1 in this matrix on my MATLAB demonstrates how page 1 is one of 4 pages pointed to by page 3 because it goes 0, 0, 1/4, and one of 2 pages pointed to by page 5 because the 5th entry in row 1 is 1/2. This matrix demonstrates this for all pages. Once you have the matrix, the next step is to determine the eigenvector of the matrix, where the eigenvalue is 1. The command bracket v comma d bracket equals eig returns a matrix V where each column is an eigenvector and a diagonal matrix D where each entry on the diagonal is the eigenvalue corresponding to the columns of V. This page shows the results from the MATLAB command. The first entry on the diagonal of D is 1, which means the first column in matrix V will be the eigenvector with an eigenvalue of 1. Therefore, the first column of V shows the results of importance for our problem. So the results for our MATLAB is that with an eigenvalue of 1, the eigenvector of A such that AX equals X is X equals 0.3391, 0.4522, 0.2261, 0.5087, 0.5652, 0.2261, where the importance of page 1 is 0.3391, etc. This shows that page 5 is the most important page because its value of 0.5652 is largest. The pages are sorted in order, decreasing importance, and the algorithm would return 542136 or 542163 because 3 and 6 have equal importance.